Okay, let me get started then. So we're going to prove theorem 2. Okay, so as I said, this theorem 1 is really not really much to do with the Ricci flow. The proof didn't use the Ricci flow. But now I want to say something about the Ricci flow. So now we actually want to say that the metrics converge smoothly to a smooth Kähler metric away from these -1 curves. So to prove theorem 2, let me, for simplicity, remember that the -1 curves are all disjoint. So let's just assume there's one of them. So let's just assume that we have just one -1 curve. Assume that we have just one -1 curve. E, and then pi is a map from M to N, which maps this E to a single point. Let's call it y naught in N. Okay, this is pi. So pi sends E to y naught, and pi is a isomorphism away from E to N, away from y naught. Okay. So the first thing I want to do is I want to rewrite the Kähler-Ricci flow. So let's write the Kähler-Ricci flow, which is d dt of omega is minus the Ricci of omega, and omega at time 0 is omega naught. I want to write it as a parabolic Monge-Ampère equation, a complex Monge-Ampère. So I'm going to, in other words, write it in terms of a potential function phi. To do that, I want to define reference metrics. I want to define a reference Kähler metric, omega hat t, which is going to live in the same cohomology class as omega t, which is, by definition, so we know that this is omega naught plus t of C1 of Km. Okay. And here's what we're going to define. So I'm going to take a very specific one. It's going to be, so we know that the final one class is this pullback of, let me say that, well, yeah, I don't want to call it beta, I want to call it like omega n, where, let's say it's, okay, let me say it here. So I can write this as 1 over t, and then t minus t omega naught, plus little t times the pullback of omega n, where omega n is in beta is Kähler. And then what you see is that this is when t is 0, this corresponds to omega naught, so I'm in the right cohomology class at t is 0. And when t is equal to capital T, this one vanishes, and I end up with the pullback of omega n, which is the alpha. So this is a line in the right direction. Okay, so this is in this cohomology class. And then notice that I can rewrite this as omega naught plus t times eta, where eta is, 1 over capital T, and then the pullback of omega n plus minus omega naught. Notice that these are really Kähler metrics for all t between 0 and capital T, because this is Kähler and this is non-negative. It's the pullback of a positive form. So as long as you're strictly less than capital T, this is actually a Kähler metric. And of course it degenerates as t goes to capital T. All right. So then the Kähler-Ricci flow is equivalent to solving the following equation. I can solve the phi dt is the log of omega hat t plus, and again there's some factor of 2 pi, dd bar of phi to the n over Oh, okay. I need some volume. I need to explain what this capital omega is. Where here capital omega is a volume form. Is a volume form on M, such that if I take dd bar of log of omega, this is equal to this eta, and let's specify it so that, say, its integral is equal to 1. This normalization is not important. Okay. How do I know that I can do such a thing? Well, eta, you can see from this formula, eta has to be in the first Chern class. And the first Chern class is, I can always, dd bar log of a volume form is always in the first Chern class. So that means I can always, just by the dd bar lemma, I can always find an omega satisfying this. Okay. And phi at time 0 is just equal to 0. Okay, so let's call this star. So now I claim that the Cayley-Ricci flow is equivalent to that. I'm calling this is a complex Monge-Ampere equation, because this is like the Monge-Ampere operator, but it's parabolic. I have a defeated t. So why is it? So why is the Cayley-Ricci flow equivalent to that? So given a solution phi to star, here of course I'm assuming that omega hat t plus dd bar phi is positive. So given a solution phi to star, you see that omega of t, which is omega hat t plus dd bar phi, has, this solves, if I define this solves the Cayley-Ricci flow, because when you differentiate it, when you do ddt of this omega t, you get ddt of omega hat t, which is the eta. But then plus root minus 1 over 2 pi, and then dd bar of phi, which is phi dot, which is this. So I get dd bar, sorry, I already wrote the root minus 1. This is dd bar log of omega to the n over capital omega. But then this is exactly minus the Ricci minus dd bar log of omega, but dd bar log of omega is eta, and so you end up with just minus Ricci of omega. Okay, because dd bar log of omega to the n is just minus the Ricci, and this minus dd bar, again this is 2 pi, this minus dd bar log of omega will cancel with that eta. And then of course omega times 0 will just give me my omega hat 0, which is just omega naught. Right. And then conversely, if you have a solution of the Cayley-Ricci flow, you can find phi satisfying this. So we're going to consider this equation star. And let me write down a lemma. Okay. That's a lemma. And this is, these estimates I think are due to Tian and Zhang. So let's write down some estimates. The first is that phi is uniformly bounded. The potential phi is uniformly bounded. The second is that phi dot, which is phi dt, is bounded from above. The third is that the volume form along the Cayley-Ricci flow, so these are all depending on t, of course, is bounded above by some constant, say constant times omega naught to the n, or I could bound it by capital omega. It's just a fixed volume form. And then number 4 is that phi of t converges to some potential phi t pointwise. For some, well, I guess phi t could have some. It converges to something. This could have some singularities. But it's let me not go into it. So for some phi t, which will actually be bounded and flow is bounded with omega hat t plus dd bar phi t non-negative. where this has to be interpreted in the appropriate sense. Okay, so what's the proof? So I'm going to apply the maximum principle, and that will prove the first two. It'll just follow from a simple maximum principle argument, and then these will just follow from the first two. So let's prove that phi is bounded, and this is not difficult. Let's define a function psi to be phi minus ct, for c is a constant to be determined. Then look at the psi dt. Well, by definition, this is just the phi dt minus c. But this is log of omega hat t plus dd bar phi to the n. But notice that dd bar phi is the same as dd bar psi. Okay, this is divided by 2 pi. And that's divided by capital omega minus c. But now let's look at the point where psi achieves its maximum. Now, when psi achieves its maximum, this is where psi achieves the maximum. Let's assume that maximum occurs not at time 0. If the maximum occurred at time 0, then psi would be less than or equal to 0. It would be down. Okay. So if it does not at time 0, then it has to be bigger than or equal to 0. You're at a maximum. So either you're sort of like this, in which case you're 0, or you're at the end. Either way, you're bigger than 0. Now at the maximum, dd bar psi is less than or equal to 0 at the maximum. So this is less than log of omega hat t to the n over capital omega minus c. But on the other hand, if I look at this omega hat t to the omega hat t, it's a smooth family of 1-1 forms, so their volume forms are certainly bounded from above. So if I choose c large enough, this is less than 0 if c is large and uniform. It's a large uniform constant. Just because these are smooth 1-1 forms and the volume form is bounded from above. Well, that's a contradiction. And being a contradiction means that actually psi did achieve its maximum at time 0. So it implies actually psi did achieve a maximum at time 0, but at time 0 phi is 0 and t is 0, so actually psi is less than or equal to 0. And so that tells me that phi is bounded by constant times t, but t is less than capital T. So phi is bounded from above. So we've proved the first, but just the upper bound of phi. Okay. Yeah, I don't want to keep that. Maybe. Well, okay. Maybe I don't really need this now, so I can get rid of it. So we have the upper bound of phi. So now let's prove the lower bound of phi. For the lower bound of phi, it's slightly more complicated, but not very much. I want to define another function which I'll call theta, and this is phi plus n times t minus t times log of t minus t minus 1 plus some large constant times t. Okay, this looks like y knows about. This is just the antiderivative of log. Right? So x times log of x minus 1 is the antiderivative of log. So that's what I'm doing here. But the x is my t minus t. So now look at the minimum of theta. So at the minimum of theta, which we assume is at some t positive, what you get is that d theta dt now is bigger than 0. No, less than 0, sorry. Less than 0. But this d theta dt is phi dot, which is log of omega hat t plus dd bar. Instead of phi, I can write theta because this is just constant in space. This over capital omega. And then the derivative of this, I get minus log, n times log of t minus t. So the point is when the derivative lands on the log, you get a minus 1. And then when the derivative lands on this, so you get another minus 1 to cancel. So you get this, and then plus c. But then with the minimum, so the minimum dd bar theta, the Hessian of theta, in particular the complex Hessian, is bigger than or equal to 0, the minimum. So this is bigger than log of omega hat t to the n over capital omega. But now let's take this guy here. This is just log of t minus t to the n with a minus sign, so I can put a t minus t to the n here, plus constant. But, so now you're going to see why I put this t minus t in. Because what you see is that omega hat t is bigger, this is non-negative, so it's bigger than t minus t times omega naught. So notice that omega hat t is bigger than t minus t, well, over t times omega naught. So its nth power is bigger than, so omega hat t to the n, this is bigger than t minus t to the n times capital omega times some, so capital omega, of course, is equivalent to omega naught to the n. It's just some fixed volume form. I put a c there where c is positive. So whatever happened, so the point is this doesn't go to 0. This is bounded below. And so this is strictly positive if c is large. Contradiction, because this was less than 0. And therefore theta actually did achieve its maximum at t is 0. And so theta is bounded above by its the value at t is 0. Well, this is just bounded by some constant. And then the point is that this this thing here, you may worry about it because you have a log, but right, x times log x is bounded. So this is a bounded quantity. It doesn't go to infinity. And so that implies that sorry, not bounded. Sorry, bounded below. That's crucial. Theta is bounded below. It's bound because it's bounded below by its value at t is 0, and this value at t is 0 is just some constant, and that tells you that phi is bounded below by another constant, because this whole quantity is bounded. Okay, so that gave me the upper and now the lower bounds of phi. So we have the upper and lower bounds of phi. Right. Number 1. So now let's prove the upper bound of phi dot. I'm going to, again, use the space, since I don't need this again. So the upper bound of phi dot. So first of all, here's my phi. So let's just apply ddt to star. So notice that ddt of phi dot, when I differentiate, now the derivative of the log of determinant is just, you just get this trace. So you get the trace with respect to omega of ddt of omega hat t plus dd bar phi. And then, of course, capital omega is fixed, so I don't get anything. So I'm just using the formula for the derivative of the log of determinant. I get the trace with respect to omega hat t plus dd bar phi, which is what I'm calling omega. So I get this, but this is nothing other. So ddt of omega hat t, remember, is just, this is what we call eta. And now this trace of dd bar phi with respect to omega is just the, sorry, that's, oh, ddt of it, yeah. So I get phi dot, phi dot. And then this is the trace with respect to omega of eta. So I get that. And then we consider the quantity. This is a trick due to Tian and Zhang. You consider the following quantity. You take t times phi dot minus phi, make sure I get that right, yes, that looks right, minus nt. I consider this. So what is this? So this is, so ddt minus Laplacian of this, so see ddt minus Laplacian of phi dot, I just get this trace. So first of all, I get t times the trace with respect to omega of eta. But then the ddt could land on the t, in which case I get a plus phi dot. But then the ddt lands on the phi, I get a minus phi dot. And then the Laplacian lands on the phi, so I get plus the Laplacian of phi. And then the ddt lands on the nt, so I get minus n. But now the phi dots, of course, cancel. And the phi dot is trace with respect to omega of omega minus omega hat t. Because this is, by definition, just the trace with respect to omega of dd bar phi. But dd bar phi is just omega minus omega hat t. So I get that. This guy here is equal to this. Okay, so what does that, put that together, I get t times the trace with respect to omega of eta, and then the trace with respect to omega of omega is just the complex, so n really should be 2, right? I guess I'm writing, yeah, n is the dimension which is 2, so I could have replaced n by 2. Well, let me leave it as n. The trace with respect to omega is just the complex dimension which is 2. So it cancels that. And then all I'm left with is minus the trace with respect to omega of omega hat t. But then omega hat t, remember, is omega naught plus t eta. So it looks like I'm left with minus the trace of omega with respect to omega of omega naught, because I do omega minus omega hat t, right? Yeah, the t eta cancels, and it's left with omega naught. Okay. And this is negative. So that tells you that this cannot achieve a maximum. This cannot achieve a maximum except at t is 0. So it implies that t phi dot, and this is bounded, so in particular t phi dot is bounded, and that tells you that phi dot is actually just bounded. Well, you might worry just bounded by constant over t, but that really doesn't matter because t close to 0, I don't care. Just by short-term existence, you get some bound. And so I only care what happens when your t is close to capital T. So I get actually phi dot's bounded above. So that proves this one. And then this is trivial because it just follows from if phi dot is bounded, well, this is just log of omega to the n over capital omega, that's bounded. So 3 follows from 2. Right, this is just from 2. Just the definition of phi dot. Okay. And now, let me say something about number 4. For 4, this actually also follows from 1 and 2, because if you look at phi minus a constant times t, when you differentiate it with respect to t, this is phi dot minus c. Let's take that c to be exactly that c. It's less than 0. So that tells me that this quantity here is monotone. It's monotone decreasing. A monotone function which is bounded, because phi is bounded and t is between 0 and capital T is bounded. Well, we know from Rudin, whatever, monotone bounded functions converge. So it converges. It converges as t goes to capital T. And so you get conversions to some. Let's just define it to be, well, I guess to some psi. And so that then, but then of course CT also converges, and so that implies that phi converges to some phi t, say. Let me just ignore this question about what phi t is. Let me just say it converges to something. Okay. And it has to be bounded because these are bounded. Okay, so that's this lemma. And now I want to, right, I'm certainly going to use that, but let me erase it. So the next thing I want to do is prove that. So the next lemma is that I want to prove that omega t is bounded below by the pullback by some small constant times the pullback of omega n for some uniform constant c which is positive. And now I claim that given this, we can prove theorem 2. Okay, so given this, theorem 2 follows. Theorem 2 follows. And that's because we know that, I guess from the lemma I raised, that because we notice that the pullback of omega n, remember that pi is an isomorphism outside of E. So here you have this omega n here. It's a nice scalar metric on compact subsets away from y naught. So when you pull it back, this is a nice scalar metric on compact subsets away from E. So notice that this is a uniformly positive metric. It's a scalar metric on m minus E. Away from the exceptional curve, it is a scalar metric. And we have that, on the other hand, we know that omega n is bounded above by a constant times capital omega. So what we get from these is that on any compact subset, of m minus E, we must have that omega t is bounded below by some constant times, say, omega naught, and bounded above by some constant times omega naught. Because once you have a lower bound of omega on the end of that compact subset, you have some lower bound like this, which means that the eigenvalues of omega must be bounded below by some uniform constant. But then the determinant is bounded above, so the product of the eigenvalues is bounded above, but each one is individually bounded below, and so that means all the eigenvalues have to be bounded. But then once you have this, once you fix your compact subset, then you can apply sort of, let's say, standard parabolic theory. It tells me that actually you get C infinity estimates. C infinity estimates for omega t. So you can apply this parabolic Evans-Krylov theory, for example, and you get all the estimates. This is saying that you have uniform elasticity, and then you get all the estimates, and then that implies actually that phi must converge to phi t smoothly on compact subsets of m minus E. Once you know that you converge to something and you have all the estimates, you can apply a Zeller-Ascoli or whatever. You must have smooth convergence on compact subsets. And therefore omega t, which is omega hat t plus dd bar phi, I guess divided by 2 pi. Well, the omega hat t is a smooth family of 1-1 form, so this will converge to omega hat t plus dd bar phi t, and that's going to be a smooth scalar metric on that compact subset. So on any compact subset, you're going to get smooth convergence. Okay, so that's, which is exactly what I wanted to show. That I get smooth convergence, and this is what I'll call omega t. Okay, so it comes down to proving this lemma. Well, I kind of want to keep that, but maybe, well, maybe I won't. Okay. So, to prove the lemma, let me cheat a bit and just let me call this a lemma. So let me call these sort of classical estimates. Although this is a bit of a misnomer, really. The first one, they're at least they're analogues of classical estimates. The first one is at least in some form in Huaidong Zhao's paper, and that is that this is true for any solution of the Cayley-Ricci flow. You don't have any assumption, so just m omega naught. Okay, so omega t solves the Cayley-Ricci flow. Just ddt of omega is minus Ricci omega. Omega 0 is omega naught. And then we have this estimate that ddt minus the Laplacian of the log, and let me say this is classical. I mean, this also, the elliptic version is in papers of Yao and Orban. So, in that sense, it's kind of classical that this quantity is bounded by a constant and then the trace of omega naught, where C depends only on the. So this depends only on the lower bound of the bisectional curvature of omega naught. So it depends. Let's just say it depends only on omega naught. I don't really care what it depends on exactly. Okay. And then number 2. This again, it goes back even before Yao, I think, but in this version, the parabolic version, is due to Song and Tian, and this is known as the parabolic Schwarz lemma, and that says that if you have any map from F to, say, from M to M prime, it's holomorphic, and then omega is scalar. Omega prime is scalar on M prime. No, I don't really like prime. Let me call it tilde. Then we have the ddt minus Laplacian of the log of the trace with respect to omega of the pullback of this omega tilde is bounded by a constant times the trace with respect to omega of the pullback of omega tilde, where this depends only on the curvature of omega tilde. Depends only on the curvature of omega tilde. Okay, so this is not. I mean, can't we call it classical? This is from only about 10 years ago. This is the so-called parabolic Schwarz lemma, but it at least has its origins, just as this one in older works. So I'm not going to prove this. So you can, I mean, in my lecture notes with Jan Song, we prove these in detail, and they're available in many other places too. So I'm going to skip the proof. And now I can prove the lemma. Okay. And then maybe we'll call it a day. Okay, so the proof of the lemma. Proof of the lemma. So what we do is I'm not really going to use this one. I'm going to use this one here. So of course we have a map pi from M to N, and we have a calorimetric. So what I can do is I want to consider the following quantity. I want to define Q to be the log of the trace of omega with respect to the pullback of omega n minus a times phi minus a n times capital T minus T, the same quantity as before, this log of capital T minus T minus 1. Take that quantity. And now I want to consider dt minus Laplacian of q. I want to show that this is, see what I want is show that this is bounded above. These things are bounded. We already showed that phi is bounded. I know this is bounded. X log x is bounded. So I want to get an upper bound for q. So at the maximum, so this is at the max of q, assuming it occurs at a point where t is positive. This is bigger than 0. But on the other hand, by this number 2, dt minus Laplacian of this log is bounded by a constant times the trace with respect to omega of the pullback of omega n. But then we have minus a phi dot. And remember, what is phi dot? It's log of omega to the n over capital omega. And now, then I have plus a times the Laplacian of phi. And then I get ddt of this, which should be plus, I think, plus log a times n times the log of capital T minus t. I claim I get that. Okay. Now I've actually used what I needed from this. So let me erase this. And now, okay. So this, first of all, notice, so we already used this before. This Laplacian of phi is just a trace with respect to omega of omega minus omega hat t. Okay. And now, what I want to do is I've got an upper bound here. I get a good term, which is like capital A times minus the trace with respect to omega of omega hat t. But notice that omega hat t, I want to choose A large enough, A is some constant, that I'm going to choose A large so that A times, or A minus 1 times omega hat t it bounds, I want to kill this term. It's bigger than constant plus 1 times the pullback of omega n. And I can certainly do that because omega hat t, this is just a nice calorimetric, and this is the pullback of omega n. So certainly each one is bigger than a little constant times the pullback of omega n. And so I can just choose the A very large, and this is certainly true. Okay, so that's going to kill this term with a bit to spare. So what I get is 0 is less than this dt minus Laplacian of q. And this is less than, I get an extra term, minus the trace with respect to omega of the pullback of omega n. And now this term here, let me change the minus to a plus. So I get plus a of log of capital omega over omega to the n. Oh, right. Capital omega times t minus t to the n. And then I get, this gives me the dimension, which is, of course, 2, but I'll just call it n. N is the complex dimension. And then I'm left with, so I just took an a minus 1, so I'm still left with a little bit. So I'm left with minus the trace with respect to omega of omega hat t. Okay. So now I want to claim that these two terms are bounded from above when you sum them up. And that's not difficult to see, because notice that that this trace with respect to omega of omega hat t, this is bigger than the trace, t minus t over capital T times the trace with respect to omega of omega naught. And that's just because omega hat t is bounded below, at least by this guy, because this is not negative. But now I can apply the arithmetic geometric mean inequality, which tells me that this is bounded below by omega 0 to the n over omega to the n to the power 1 over n. Maybe there's some factor n there. Okay, here this is like, think of the eigenvalues of omega as like lambda 1 to lambda n. Think of this as the identity. It's like 1 over lambda 1 plus 1 over lambda 2. That's just 2, right? And then, so n here is just 2, of course. But then the arithmetic geometric mean inequality says 1 over lambda 1 plus 1 over lambda 2 is bigger than 1 over lambda 1 times lambda 2 to the 1/2. So I get this. And then there's a factor of t minus t as well. Okay, so let me put that inside. T minus t to the n to the 1 over n. But then this looks an awful lot like this guy here. So this is, there's a factor of 1 over t here. Okay, so the whole thing is bigger than some small constant times capital omega t minus t to the n over omega to the n, all to the power 1 over n. So now this tells me that this thing is bounded by minus trace, let's write the same thing again, omega n plus the an. I don't care about the an, it's just some constant. And then I have plus a times log of this guy over omega to the n. And then minus the small constant, which is uniform, times the same thing to the power 1 over n. Okay. And then I want to get that this thing is bounded above. But that's true because recall that the function a times x, a times log of x minus a constant times x to the 1 over n is always going to be bounded above. So c is a positive constant for x positive. Just because, if x goes to 0, of course this goes to negative infinity. When x is large, this is like log, but this is a power, so it's better. It beats it. This is always bounded above. Okay, so the whole thing then is bounded above by minus trace omega of the pullback of omega n plus some constant, let's call it c prime, which is just this constant plus this constant. But then you're done, because what you then see is that, let me get rid of this. So we see that at the maximum of q, we get that this quantity here, this trace omega pullback of omega n, is bounded from above. But that tells me that the q is bounded from above. Q is bounded from above. So if it's bounded above at its maximum, it's bounded above everywhere, and therefore the Q is bounded, and that's exactly what we want to show. This is bounded above, which tells me that omega t must be bounded below by this. Okay. So then we're done. So we proved the lemma. Okay, so that completes the proof of this theorem too. So what I want, maybe that's a good place to start, but what I want to do next time is explain some more tricky estimates. Is I want to really know what's actually happening near the exceptional curves. So that's where it gets a bit more tricky. So I'll talk about that on Thursday. Okay, thanks.